Thanks for attending another one of these tutorials or recitations on the force method versus the method of Stroops. Here we compare the force method with a newly developed method, the method of Stroops. Students of structural analysis or statics can compare the two methods and decide which one they prefer. Methods that have been taught for generations may not always be the most efficient or understandable. I know many of you who are students of structural analysis are focused on the force method. You just want to learn the force method because that's what's on the syllabus. Something like the method of Stroops is not on the syllabus, so you may not be interested in it, but I'm asking you to spend time here looking at another method. It will give you a perspective. Part of your education is learning to think critically, and it's good to compare two approaches of solving the same problem. Anyway, I'm getting off script. My name is Charles DeMatteis. I am a retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad. The university provides support for my video creation. It provides a workspace and other benefits. I hope that this video meets the standards expected by a university of the caliber of the University of the West Indies. The problem we are solving in this video is taken from another video, Essay 26, Force Method, Truss Analysis, from approximately 9 minutes 30 seconds into that video. Here we have a truss with 4 joints, A, B, C, D, and 6 members. Basically, it's 5 meters spacing of these joints and 4 meters vertically in this direction between A and B. There is a hinge joint at A, so this cannot move vertically or horizontally, but rotation is possible. It's on rollers at B, so this joint can move horizontally but not vertically. One load is applied at D, 10 kilonewtons vertically. All members have equal areas of cross section. We will apply the method of Stroops to analyze this truss. And the method of Stroops was developed in my video, Trusses, Electrical Circuits, and Kirchhoff's Laws. And I have used the method of Stroops in other videos. So you can look at this video. You can wait until after viewing this video, and you'll get more details of the method of Stroops from this video. My name is Charles DeMatteis. I am a retired lecturer from the University of the West Indies, St. Augustine campus in Trinidad. And the university provides workspace and other support for my video creation, so I will give due credit to the university. The first step, as usual, is to find the transfer of forces from the loads to the supports. And in this case we will start at D, and there's a vertical load of 10 kilonewtons, so the force in BD cannot balance this 10 kilonewtons because it's at right angles to it. But so you have to look at the vertical component in one of these other members. We'll assume that the member CD takes all of that vertical component of 10 kilonewtons. So the force in this member will be tensile force of 5 root 41 over 2 kilonewtons. So that the vertical component of this member CD will balance the 10 kilonewtons. But of course this tensile force will have a horizontal component also, and this will be balanced by a compressive force in BD of minus 25 over 2 kilonewtons. And then you can look at the joint C. This force of 5 root 41 over 2 kilonewtons in CD has to be balanced horizontally, and the force in AC will be a tensile force of 25 over 2 kilonewtons. And of course the vertical component of CD must be balanced by the force in BC. So BC has to be a compressive force of 10 kilonewtons. And when you look at this is on rollers, so the horizontal components must cancel each other. So the force in this direction of 25 kilonewtons has to balance the horizontal component of AB. So AB has to be minus 5 square root of 41 over 2. And this will transfer the load here, 10 kilonewtons, to the supports. Now effectively what I've done is I have removed this member AD. You would obtain the same result if you had obtained a primary structure by removing AD, and you'd get these forces in the other members. But there's no unique way of doing this. I could have also transferred the vertical component here entirely to this member AD, and then these three members would have zero force. And I could have done it other ways, okay? So I could have had only forces in this member, and this member. That would have done it also. But in this case, I've just chosen to use this configuration. The next step is to include the stroop forces. There is just one stroop in this structure, which is the entire truss ABCD and the 6 members. And this is a parallelogram. And for parallelograms, a rectangle, of course, is included in this statement. For a parallelogram, the stroop forces are very easy to write down. That's because the stroop forces are proportional to the lengths of the members. You can just verify here that this diagonal member will have length square root of 116. This member AC and BD have length 5, and these other members have lengths square root of 41. So, and of course the diagonals here have the respective lengths. So this is a parallelogram, and the stroop forces are parallel to the lengths of the members in the parallelogram. So this is a consequence of the fact that forces add up according to the parallelogram law, and that's why when you have forces along the sides of the parallelogram, those forces are proportional to the lengths of those sides. So it's quite easy to write down the stroop forces for a parallelogram. So we superpose the last two diagrams. It was 25/2 plus the stroop force 5F, 5/2 root 41 here, plus the stroop force root 41F, etc. The transferred force plus the stroop force, etc. We obtain these forces in the members. On the diagonal, it's 0 plus this stroop force minus root 116F. So these are superposed from the previous two diagrams. The compatibility equation for this type of stroop is, again, the terms here are of the same form: square of the length of the member over the cross-sectional area of the member times the force in that member. And it's the summation around the perimeter equated to the summation on the diagonals. Again, this is the same form of compatibility equation that we obtained for a rectangle, and the same form is valid for parallelograms. So again, you have the compatibility equation for the parallelogram, very easy to write down. Okay, so that's why this method of stroop forces works quite well when you have stroops that are in the form of rectangles or parallelograms. Both the stroop forces and the compatibility equations are quite easy to write down. Anyway, let's go ahead. As we said in the initial slide, the area of cross-section is the same for all members, so these areas can be taken out as a common factor and cancelled. So the compatibility equation reduces to this form, where the coefficients are the squares of the relative member lengths. As we said in other videos, we need only to work with relative member lengths, not actual member lengths. And these are the coefficients of the compatibility equation. Basically, it's just the square of the member lengths. Okay, so this member length was square root of 41. The square is simply 41. 41 here also. The member length on this diagonal was square root of 116. The square is just 116. 4 squared is 16, and then you have 5 squared, 5 squared. So the coefficients are the squares of the lengths of the members. Again, very easy to write down. And one thing again is that I haven't put in any minus signs here. That's because I express the compatibility equation as the sum around the perimeter equal to the sum on the diagonals. So in that equation, all of the coefficients are positive. If I had put everything on one side equal to 0, then I'd have to have negative coefficients here. But I want to avoid putting in negative signs, because it's the easiest mistake to make in these kinds of calculations is with a minus sign, a negative sign. It's easy to forget a minus sign or make an error in putting in these signs. So let's go ahead. So I've just juxtaposed the last two diagrams here. I have the coefficients here and I have the superposed forces. We are going to multiply the corresponding coefficients with the superposed forces. Corresponding coefficients with the superposed forces. It's customary to write up tables with the list of members and the coefficients, etc., etc., but I'm just going to put everything on a diagram, and I think it's easier to see what is happening when you have everything on a diagram instead of the table form. So let's go through it. You have 25 into this. This is the coefficient here times the superposed forces, plus 25 times this, 25 times this, that's another term, and then 41 times this, 41 times this superposed force, and then 41 times this superposed force. So that's the sum around the perimeter, and you equate that to the sum on the diagonals. It's 16 times minus 10 minus 4f, and then plus 16 times negative square root of 116f. So that's our compatibility equation. So on the first line here, first two lines, I've just transcribed from the previous slide. No changes have been made here. Now I will put all of the f's on one side and the constant on the right hand side. So each of these have f. So this gives you f equal to minus 160. And minus 160. I think there's a minus sign missing here. Okay, it should be a minus here. I'll change that on this slide. Okay, I don't have time to go back and change that, so but just note there should be a minus sign. Okay, 16 by negative 10 should have a minus sign here, and this will work out. When you calculate f, you get minus 0.0766. Now once you have f, you can substitute into the diagram with the superposed forces, and this will give you the solution to the truss. Alright, so here's the solution. I've worked it out in decimal form. Minus 10 here, you have tensile force 0.825 here, tensile force here, compressive, 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 tensile here. And these are the same values except for minor errors as in the video. Okay, in the video where it's done using the force method, there are some minor errors, I think with this minus 12.88. You can read the comments in that video, and someone pointed out in the comments there are some slight errors, but these values should be correct to these decimal places. So once again, this verifies that the method of Stroops gives the correct answers, because this solution matches the solution obtained by the force method. Okay, so I need to convince you of that the method of Stroops is a valid method. It gives correct results, and you can depend on it, and you can make a decision which method you prefer. I personally struggle with the force method. I find it's very difficult to remember and to apply, but I think the method of Stroops should be taught in place of the force method. I think it's a much cleaner method, if you want to use that term, and I think there are less calculations involved. As usual, I give a little extra analysis for the method of Stroops. In the previous analysis, it was assumed that all of the areas of cross-section were the same. But let's suppose we had this arrangement. We decided to have the same areas of cross-section on the perimeter. A1 on the perimeter, and the diagonal members, this is a shorter diagonal, so let's suppose this has area A2, the longer diagonal with area A3. Suppose we wanted to do a different design with different cross-sectional areas in this form. And then the coefficients of the compatibility equation would be these. Remember, in the previous statements we made, when all of the areas were equal, we could have cancelled them or factored them out and just get the squares of the lengths as the coefficients. But when you have different areas of cross-section, you have to include those areas in the coefficients. So it's the square of the length divided by the cross-sectional area. So it's A1 on the perimeter, A2 on this diagonal, and A3 on this diagonal. So the square of the length is divided by the area of cross-section. Again, I've juxtaposed two diagrams here, the coefficients and the superposed forces here. And we do the same thing to get the compatibility equation. Coefficient times force, sum those terms on the perimeter, and then equate to the coefficient times force on the two diagonals. So when you do that, the compatibility equation turns out to be this. You have these four terms on the perimeter equal to these terms on the diagonals. And again, we collect similar terms. These are the terms including F on the left hand side, equal the constant term, the term without F on the right hand side. Notice it is a negative 160 here. That shows there was an error in the previous computation that I did. And again, you simplify. What I've done here is I've combined terms here. What I've done here is I've divided throughout by F. I've put the F in the denominator here. So I've divided everything throughout by F. And you get this thing equal to this. And then what we do, we divide by we divide by, we multiply throughout by A2. So you get this term times A2 over A1 plus this term by A2 over A3. Now when you multiply by A2, this just becomes 64, and you take that across, so you get minus 64 minus 160 over F. Right, so again we do these manipulations to get this result. Notice here we have the ratios of the areas, A2 over A1 and A2 over A3. So these are related in this linear fashion. Again, this line is just transcribed from the bottom of the previous slide. And suppose we wanted F to be minus 0.08. The value of F that we calculated previously was close to 0.08. So let's use this. Let's assume F is 0.08. We are just going to use a value of F close to what we obtained when we assumed equal areas. So you put F equal to 0.08. This works out to be about 2000, I think, and then 2000 minus 64 is 1936. So you get this equal to 1936. Divide by 1936 and simplify, you get A2 over A1 equal to 2.5, let's say, plus A2 over A3 over 1.55 equal to 1. Again, this is a straight line relationship between A2 over A1 and A2 over A3. If you plot these variables, if you draw the straight line with this variable against this variable, the intercepts will be these numbers, 2.49 and 1.55 on the diagonals. Right, so here I plot the A2 over A3 against A2 over A1. It's about 1.55 on intercept on this axis and about 2.5 intercept on this axis, and connected by a straight line. Now we would like the A2 to be less than the A1. So here I'm selecting a value A2 over A1 to be 0.5, and I read off the corresponding value of A2 over A3. This is a good choice also. Value greater than 1 for A2 over A3 means that the A2 is larger than the A3. A2 larger than the A3. So here we have the A3 smaller than the A2, which is okay. Alright, so the A2 is larger here, and the A2 is larger than the A2 of 0.5. This value means that the A2 is smaller than the A1, and this makes a good design for us. So if you look up your cross-sectional areas for standard steel sections, you try to get ratios in this with these values. Okay, 0.5 for this ratio and about 1.2 for this ratio, and that will give you force that you can easily calculate using the F equal to 0.08. So this is how you can use the compatibility equation for design, not just for analysis. Thanks again for getting through this video, and please leave comments and share this video. Let me know what topics you'd like me to cover in using the method of Stroops, and whether you find this method helpful. Again, I am not convinced that the force method of virtual work and these things, I'm not convinced that these are the best ways of handling indeterminate trusses and other indeterminate structures. I think the method of Stroops is much better, and it gives a few extras. So again, my name is Charles DeMatteis, retired lecturer from the University of the West Indies, St. Augustine campus, Trinidad, and I give credit to the university for helping me with these videos. They provided me with a workspace and other support. Thanks again for your attention.